Alright, so we're going to let A be the integers, m is z mod mz, n is z mod nz. Prove that this tensor product is isomorphic to this quotient. So we're going to refer to elements of these quotients by coset representatives, just because I find that the most natural. Like, you refer to elements of z mod kz, I'll just label them 0 through k minus 1. So now let D be the greatest common divisor of m and n. So let's start with the map from here to here. The simplest thing we can think of. We take x comma y and we send it to xy. We got to prove that's well defined. And the reason that is that if you consider what happens to x comma y is going to go to xy. But what if you're considering like another coset representative, i.e. you consider x plus km for some integer k? Then this is going to get sent to by distributivity. It's going to be xy plus kmy, but this is in z mod GCD of z, and so what happens is D divides, since D is the greatest common divisor of m and n, D divides m, and so m here is a multiple of D, and so this whole element is 0, or this whole term here is 0, whatever you want to call it. And so, this is just xy, and so it's well defined. It doesn't matter what coset representative we use. What else? Certainly it's bilinear over z, because if you take if you multiply, it's just commutativity of multiplication on the integers. If you take an integer k times x comma y, that'll give you kxy, and if you take an x comma ky, that will go to xky, and of course those two are the same thing. So that's that. And also, if you have x1 plus x2 comma y, then that being the same as x1 comma y plus x2 comma y, that's just distributivity. So that's bilinearity. Therefore, by the universal property of this tensor product, there is a unique map phi that goes from this tensor product to z mod dz, which sends phi of x tensor y to xy. Or I think in one of the other problems, the way I wrote this was that we had a map that sent there's another problem where I use this universal property thingy, but if you go back and you compare the definitions, it's literally the exact same thing. There's some more functions hidden in here, because really what this should be is this map applied to x comma y, which of course sends to x times y, and then it should be phi composed with the map that sends the ordered pair x comma y to the element x tensor y. But if you give those functions all names, then it ends up being exactly this. Alright, so we have this map here. So that's good. And it's also going to be bilinear by the universal property. Alright, so what do we want? We want this to be an isomorphism. So let's prove that. Let's say we take any element here in this tensor product. Then, because of bilinearity, you can pull out x and y, and this is just xy times 1 should be the tensor product of 1 and 1. Therefore, the tensor product of m and n is generated by this particular element, because any element in here looks like this and can be written as a multiple of this. So that's what that means. So let R be the order of this element. And we want to prove that R equals D, because if R equals D, then these two sets must have the same size, and because phi is a because it's a bilinear map. Well, is it bilinear or just linear? I think it's just linear because yeah, the bilinearity is when you're going from m times n to here. But you've sort of got bilinearity sort of built into this, so I think this is just linearity. So we know that phi is a linear map, and that makes sense because z mod dz, there's no bilinearity there, so it doesn't make sense for there to be any bilinearity here. Okay, so we know that phi is a linear map, and if it's if it's bijective, then it's an isomorphism. And if these two sets have the same size, and in particular they're finite, then the map between them must be well, since m tensor n is generated by 1 tensor 1, which has order r, that means that this tensor product has order r. And obviously z mod dz has order d. And so if these two things have the same size, then what does that tell us about phi? So I think we need to use something else here. We need to use that either like a surjection between maps of the same size. Okay, well, let's do it this way. Obviously, is it obvious that this is going to be surjective or injective? I think that what we want to do here is, since they're the same size, all we need is either injectivity or surjectivity, and then they're automatically phi is automatically an isomorphism. So let's see which of those would be easier. What if we take phi of 0 tensor 0. Well, let's say that phi of x tensor y equals 0. This means that xy is 0, which means that either x is going to divide x is going to divide d, or y is going to divide d. Is that it, or is it d divides x or d divides y? One of x and y has to be a multiple of d. So d divides x, or d divides y. So if d divides x, then we can factor out a d. Then x tensor y is going to be d times something tensor something. or let's say, yeah, z. Let's assume, without loss of generality, that d divides x, and it should work. So x tensor y is this divide is this, and then d is the order of 1 tensor 1. So we can, so this is z times y times d of 1 tensor 1, which is z, but d is the order of 1 tensor 1, right? No, d is r. D is r. So this is going to be equal to z times y times r times 1 tensor 1. That's going to be z times y times 0 equals 0. Okay, so if r equals d, then it's easy to prove that phi is injective, and because you've got an injective map between two sets of the same size, it's automatically surjective, and therefore it's bijective. Okay, so I guess there's a lot of steps I need to, or a couple steps I need to add in here, between saying that these sets are the same size and then saying that phi is a bijection. I feel like there should be like a one sentence thing that takes us like from here to automatically giving us bijectivity. There's probably something that I'm just blanking out on right now. There's probably a very easy solution, but this certainly is also a solution. It just might not be a good solution if it happens to be that I'm just sort of running around in circles a little bit and not taking a direct path to the final answer, if that sort of makes sense. But anyway, so let's just prove that r is equal to d. So m of 1 tensor 1, this is m tensor 1. Well, this is 0 times 1 because this first coordinate is in z mod mz. And that's just 0 because of bilinearity of tensor products, because that's how tensor products work. We know that r divides m because we know that multiplying 1 tensor 1 by m. So yeah, the order the order of 1 times 1 has to divide m because m times this is 0. And similarly, we do the same thing with n, but here we move the n into the second coordinate, and that's going to give us 0. And so r divides m, and since r divides both m and n, it divides d. Next, you have 0 is phi of 0, which is phi of r of 1 tensor 1, and because of linearity, you can bring out the r, and this is just r times 1 equals r. So r equals 1, and where does this take place? This is taking place in z mod dz, because of course here we're thinking of phi of 0 and r as elements in the image of phi, which is z mod dz. And so for 0 to equal r in z mod dz, that means that d must divide r. So if r divides d and d divides r, that means that r equals d. And therefore, once you have that, you can prove that phi is an isomorphism, and then phi must also, no, you can prove that phi is injective, and then it follows automatically that phi is surjective, and therefore phi is bijective, and combining that with linearity gives you that it's an isomorphism, and that finishes the proof.